In this video, we're going to talk about Gauss's law, which is one of Maxwell's four equations that underline the classical interpretation of electricity and magnetism. And what we're really going to focus on is how we can use vector calculus, and in particular the divergence theorem from vector calculus, to derive Gauss's law. Now, where I'm going to jump in my derivation of Gauss's law is actually a statement that we saw in the previous video when we were talking about the divergence theorem. And what we saw was that when you had zero divergence, which is a property that we're going to have for electric fields, then if you had two different surfaces that were surrounding the same point, the flux across both of those surfaces is the same. That was a consequence of the divergence theorem. We're going to make use of that in this video when we want to talk about the flux of an electric field across an arbitrary surface. We're going to compare that to the flux of the electric field across a much simpler surface, a sphere of radius a. And then we're going to be able to use this property to say that the flux across the two surfaces, the arbitrary one you've been given, and the nice one that we can use for computations easily, is in fact the same. And then I'm going to give an example, and in my example, I'm going to give an electric field. Maybe I'll ignore the constants, but I'm going to imagine that my field is x in the I hat, y in the j hat, and z in the k hat. So that is, it's kind of like a source field. It's pointing out at every point. And then I'm going to divide it out by r cubed here, where r is the familiar square root of x squared plus y squared plus z squared. And this type of field represents the electric field and the gravitational field. I'm sort of imagining that I've got like a little particle here, and I'm pointing out an electric field at all spots, and it's going out in this direction. And it has a magnitude of 1 over r squared dependency. 1 over r cubed in the field, but when you take the length of the field, you get 1 more r on the top. So it cancels out to 1 over r squared dependency. If it was an electric field, it would have some constant in front of it. If it was a gravitational field, it would have a different constant in front of it. But either way, we have this f. Next thing I want to tell you about is the gradient of that f is equal to 0. Now, this is actually a little bit non-trivial, but it's just an exercise, so I'm actually going to leave that for you to do. Compute out the divergence, make sure that everything does cancel, and give exactly 0. I'm just going to use that property here because what we talked about earlier, when we talked about divergence theorem and multiple different surfaces, well, that was using that the divergence was 0. And indeed, this field is an example of one that has a 0 divergence. Now, what we're going to do here when we use the divergence theorem is we had just talked about how if the divergence was 0, which is true in this particular field, so true for electric fields and gravitational fields, then we have this really nice property of the flux across one surface being the exact same thing as the flux across a very different surface. So in the scenario where you have an inside surface and an outside surface, and it has this region in between where the divergence is 0 on that region, then the flux across the inside surface and the flux across the outside surface is just the same thing. So we're going to make use of that particular property. And the big way to make use of this property is to do this computation of flux for one nice surface, and then say it's true for any surface. So for example, if I have my little point particle that's going to generate some electric field, I can compute a nice surface being what I will call SA. I used to call it S1, but maybe we'll call this the sphere of radius A, a specific nice surface. And then, who knows, I have some other weird surface that's larger than it that encloses this small little sphere of radius A. The argument is going to be, by the divergence theorem, the flux across this small little sphere, the sphere of radius A, is the same thing as the flux across this arbitrary big surface. So let's do the flux across the sphere of radius A first. I'm going to compute the surface integral over SA, the specific surface that is the sphere of radius A. Maybe I'll write that in. Sphere of radius A. Centered at the origin, which is where I'm going to imagine my point particle is placed. So wherever you have your particle, we'll call that the origin. We're doing a small sphere of radius A about that, of my F dotted with N, and then I'm going to integrate that out d sigma. So what's the normal? That's the one that I'm going to have to focus on. So this normal is, well, I could do the gradient of G over the length of the gradient of G. My surface is described as x squared plus y squared plus z squared is equal to a squared. Well, that's my surface. My G is x squared plus y squared plus z squared. and then I'm setting that to be equal to a squared if it's going to be the sphere of radius a. And so this normal is going to give me a 2x, 2y, 2z, and then when I'm going to divide this out by the length of this thing, actually it's going to look like all the 2's are going to cancel, so I'm just going to erase them anyways. And that's going to give me a square root of x squared plus y squared plus z squared. I would have had a 2 on the bottom, so they would have canceled all the 2's. Okay, then what do I want to do? Well, I've got my n here. Let me just remind me about my f for a moment. So my f was, if I remember correctly, x, y, z, and then divided out by r cubed. Indeed, I'll notice that what we have on the bottom here is an r as well. So then, if I actually want to compute out what this integral is going to be, so this is going to be the double integral over the sphere of radius a. Let's actually compute the f dot n. So they've got the same numerator, x, y, z in the three components. So that in the dot product is an x squared plus y squared plus z squared. Then the f has r cubed on the bottom, the n has r on the bottom. Along the surface of radius a, we'll say r is equal to a. So this is just going to be divided out by a cubed from the first, and then a from the second is all an a to the fourth, and then integrated d sigma. What's the numerator? Well, the numerator, that's just a squared on the surface of a sphere of radius a. We'll again call r equal to a. So what does this look like? It looks like 1 over a squared, the surface integral of a sphere of radius a d sigma, that's now just the surface area. And so we know the surface area of a sphere of radius a, it is, well, 1 over a squared comes at the front, and then it is 4 pi the radius squared, the a squareds cancel, and I'm just left with 4 pi. All right, so we're almost ready for our big moment, our grand reveal of Gauss's law. We have computed that the flux of this particular field across a small sphere of radius a is 4 pi. However, if I go back up again to what we had talked about previously, it was that if I have the flux across the sphere of radius a, which is going to be my small inside surface, and then I take some arbitrary surface that is outside of that so that there's this region in between them, then the flux across those surfaces is the same. That's the property of divergence here. When the divergence is 0, the two different fluxes are the same. So now we're just about ready to state Gauss's law here. So let's get ourselves a little bit of space. I'll leave that 4 pi conclusion there. And let's go for bright yellow just because I'm a little bit excited right now. So the electric field is equal to Q, which is a constant that stands for the charge of your particle, divided by 4 pi epsilon naught. Epsilon naught is another constant. It's the permittivity of free space or of vacuum space times the field that we had just described. And then what we can conclude from what we've talked about is that if I want to go and compute a surface integral, any generic surface that you wish, well, it does have to be nice enough to satisfy the conditions of the theorem we've talking about. So we need to have some nice, smooth outside surface S, which has this small sphere of radius a around the point charge located at the origin inside of it. Regardless, if I want to figure out what the outward flux of that electric field is going to be, so this is the surface integral along your arbitrary surface, then by what we've just done, we can say that for this arbitrary surface, this is just the same thing as the surface integral over the sphere of radius a, which we've just computed, of the flux dotted with n d sigma. And, well, the only thing to happen now is the electric field is almost the example we just computed. There is this new Q divided by 4 pi epsilon naught, but other than that, it's the answer we just computed, which was 4 pi. 4 pi's cancel, and I get the charge over the permittivity of free space. And that is equal to the flux across an arbitrary surface of the electric field. And so this together is called Gauss's law. It says that the flux across a surface by the electric field of this point charge is just equal to Q divided by epsilon naught. And indeed, this law is one of the 4 foundational laws of electricity and magnetism, Maxwell's equations. This is one of those 4.